And I'm going to move on to next speakers. So he's Dr. Harish Viswanathan from Nokia. And he's going to talk us about the expanding the human possibilities in the 6G era. I'm going to introduce him very briefly. He is now the head of radio systems research group in Nokia, and he joined Bell Lab in 1997 and has led investigation of various aspects of a wireless communication system. He is an IEEE fellow and also a Bell Lab fellow. So let's welcome Dr. Viswanathan.
Hi, my name is Harish Viswanathan. I lead the Radio Systems Research Lab at Nokia Bell Labs. Thank you for inviting me to speak at this conference. Today I'm going to be speaking about Nokia's vision for 6G and some of the essential technologies that we believe will be part of 6G. Let's begin by taking a historical perspective on the previous generations. 2G and 3G were really about enabling voice and mobility. For the first time, most of us could speak from anywhere that we wanted to. While 3G started the broadband introduction, it really took off in 4G. So you could say that 4G was about unleashing the potential of information and social interaction. New applications for these social engagement were created and made available to the smartphones. We are at the beginning of 5G, and the goal for 5G has been the introduction of cellular technology to industries. Industrial Internet of Things is touted as the major application. So one could argue that 5G will eventually be about unleashing the potential of machines and sensors. What will 6G be about? We believe 6G should be about unleashing the potential of humans, expanding the possibility for humans. Our view of humans in the 2030s to 2040s involves the physical, digital, and the human world, so to speak. So the digital world will be a high-resolution, real-time representation of the physical world. It will also be multimodal, multisensory in nature. And the human world refers to the physiological parameters that will then be represented in the digital world. It could also be about capturing human emotions in the digital world. And we will not only inhabit the physical world, but we will also inhabit the digital world. And so the role of 6G is really about interconnecting these different worlds that we are going to be part of in a seamless and real-time manner. In terms of unleashing human potential, we believe that there are three broad categories of use cases that 6G will enable. The first one is enriching experience. So this is all about the creation of these dynamic digital worlds, and that may be the new framework for applications of the future, such as telepresence, as well as remote collaboration of factory workers to do digital co-design. Then there will be applications related to augmenting human intelligence. We will have more machines driven by artificial intelligence, more devices driven by artificial intelligence, the digital assistants of today being early versions of what we will actually see in the future. And the 6G connectivity has to enable the communication needs for such devices, including their training and their computing, meeting their computing needs, which may be in different locations. And it will truly enhance human intelligence in the sense that it will provide us with situational awareness all the time. It can provide us more security, and we will learn more about the human body itself through new sensing technologies. Finally, 6G will be about enhancing human productivity. We should be able to offload tasks to machines according to our wish. Usually the routine tasks that humans do not like to do, but perhaps more intelligent tasks as well as the machines become more intelligent. So we expect more robots that will cooperatively work to achieve many different tasks, both in factories as well as at home. And the 6G connectivity should enable the control of these robots within the digital world seamlessly by humans. It could also be things like remote driving, where self-driving is not feasible. You may be engaged in remote driving, which requires reliable and low latency connectivity. To summarize, 6G is about connecting the digital, physical, and the human world in a seamless way and extending our experience across these different worlds. How is 6G really going to be different from 5G? This is a question that several of us have. I would like to address that in the context of wide area on this slide and local area or campus on the next slide. What I've listed is a set of features that 5G networks will have, and I've looked at how they may evolve in 6G and what are the technology enablers that will take us from 5G to 6G. The first one is the kind of applications that 5G is enabling. We all know that 5G has been designed for supporting enhanced mobile broadband, and if you look at what the use cases, new use cases that it's likely to enable, they're revolving around augmented reality gaming or other applications of augmented reality, more connected infotainment in vehicles, etc. And if you look at what this means, what this translates to in the 6G timeframe, it will be the dynamic digital worlds that we talked about, not just augmented reality, but entire physical worlds represented in the digital world. And the means to get there is through new spectrum with extreme MIMO and machine learning as tools to achieve these higher capacities in a wide area context. In 5G, we have remote monitoring and guidance of new industrial Internet of Things robots and drones. It's still mostly monitoring and occasional guidance, but in 6G, this will evolve to true remote control with or without human in the loop. And this is enabled by higher reliability networks. Coverage in 5G is still patchy in the sense that if you go out into the rural areas, we don't have continuous coverage for cellular networks as a whole, and we don't have coverage over oceans. What we believe is by the time of 6G, we will have true global coverage with the help of non-terrestrial networks, which will then be integrated or will interoperate with terrestrial networks. And expanding to the rural areas may also include new spectrum sharing and RAN sharing mechanisms to make it economical. We already have self-optimizing networks from the 4G days, and they're actively being used and deployed in 5G as well. The next step in this evolution is zero-touch automation. Truly designing the network to learn and analyze the root causes and take action all automatically without human intervention. And machine learning will serve as the primary tool that will take us to this state of the network. And energy efficiency will become a critical factor, and automation will also focus on making sure that our networks operate in the most energy efficient manner. 5G networks are starting to be deployed in a cloud native manner in the edge cloud and the core cloud. Microservices, virtualized network functions are the norm. And if you think about what this will evolve to in the 6G timeframe, we are likely to go to more heterogeneous cloud environments. So we may be relying on not just telco clouds, but also public clouds, private clouds, hybrid versions of those, and on-premise clouds. And the network functions will be distributed across these as necessary. The architecture has opportunities to be further simplified as we move to this cloud-based deployment. We can combine functions or design the network to avoid duplication of functionality and make the architecture simpler. At the same time, we have to enable specialization so that the network can be deployed for a variety of different applications. Finally, secure. We have designed 5G to be secure. We have incorporated many different protocols. The next step for that in 6G will be to make networks truly trustworthy and resilient. Trustworthy means that we trust the software that's used to design or to implement our networks. The software may come from different vendors in a multi-vendor network. Tools such as automated software verification may enable creating these truly trustworthy networks. At the same time, we'll have new security and privacy techniques and mesh network technologies to enable resilient networks, networks that are resilient against natural disasters as well as security attacks. The 6G networks will also be optimized for private wireless deployments in a campus or a local area context. I've highlighted in blue the themes that are distinct for industrial networks compared to the wide area networks. The first one is the ultra reliable low latency capability of 5G will be further extended in 6G. We can expect that to be optimized using new technologies such as joint communication and control design to leverage the real need for low latency and reliability for the applications. So we can expect in some cases sub-millisecond latencies and higher reliability even than the 7 nines in 5G. We will employ digital twin of the factories and other environments where the networks are deployed in to optimize the network further for increasing the spectral efficiency and reducing cost. We enabled 5G with low power IoT as well as RedCap, the reduced capability of 5G for certain applications. So historically, we've been expanding the use of cellular networks from towards smaller and lower cost devices with various requirements. And another expansion of the use case will happen when we go for backscatter communications, enabling zero energy devices. So you can imagine batteryless tags that are deployed in warehouses to track assets, or it could be sensors deployed to monitor the environment in an outdoor context, which are essentially batteryless through energy harvesting or have very low power communication requirements. We can envision 6G enabling such new applications through technologies such as backscatter communications. And then localization is an important feature of 5G, which is evolving to precise localization in 5G Advanced with sub-meter precision. And in 6G, we can expect the network to do more than just localization of active devices. The network can start doing localization of passive devices. So the network not only communicates to active devices, but it also behaves like a radar and learns about the environment from the access point. So you can imagine applications such as detecting the presence of humans where they should not be, or the presence of obstructions in the path of robots, and things like that. This will be enabled by the joint communication and sensing technology and wide bandwidth carriers that we are likely to have in the 6G timeframe will facilitate such sensing applications. The rest of the features are similar between wide area and campus networks. To summarize, we can think of 6G as involving these 6 essential technologies. New spectrum technologies includes use of spectrum in new bands using extreme massive MIMO or other radio technologies. AI native air interface will be an essential ingredient in 6G. This allows better spectral efficiency and energy efficiency of the air interface, and it allows adaptation of the air interface to new scenarios. It's a new paradigm for our design of our physical layer, and it can have a big impact in terms of R&D efficiency and things like that. Network as a sensor is the joint communications and sensing that we just talked about. Extreme connectivity are the technologies needed to further optimize ultra reliable low latency communications, and can include the joint communications and control design that I just talked about. Then we have architecture, simplification, automation, and then security and trust as the other 2 major technologies to focus on for 6G. I will try to touch on the new spectrum possibilities for 6G, talk a little bit about the MIMO radio technology that we will need in the 6G timeframe, and then some aspects of the air interface design using machine learning. 6G will involve new bands with wider carriers as well as reforming of the 4G, 5G spectrum. Starting from the middle here, we believe that the 7 to 20 gigahertz band represents the golden band for 6G, the upper mid bands, where we can have significant additional capacity if the spectrum becomes available using massive MIMO technology, and will lead to new infrastructure investment from CSPs as they increase their capacity significantly. The other new spectrum possibilities include spectrum in the 90 to 250 gigahertz, or what we call the sub-terahertz range. These are primarily for short-range networks and also for sensing. The short-range networks could be for indoor or outdoor in crowded scenarios like stadiums. Then we have new spectrum, perhaps in the very low bands of 470 to 690 megahertz, where the bandwidth carriers would be narrow, and they could be used for new wide area IoT, such as the backscatter-based communications that I just talked about. Then we'll of course have reforming of the millimeter wave bands, as well as the sub-6 gigahertz bands that are being used for 5G. Overall, 6G marks a new investment cycle, and having new spectrum enables higher capacity with new infrastructure. Thinking about the new 7 to 20 gigahertz spectrum, we can fit many more antennas for the same array dimension. So what you see here is on the left, about 256 antenna elements in this 37 centimeter by 71 centimeter area in the 3.5 gigahertz band. For the same antenna dimensions, if we go to 7 gigahertz, it's possible to support 4 times as many antenna elements, twice as many in each dimension. And if we go to 14 gigahertz, we can actually do 4 times as many antenna elements in each dimension, or almost 4,000 radiators for the same antenna dimension. So there is opportunity to increase the cell capacity substantially using these extreme massive MIMO schemes. With 4x a wider bandwidth and 5x increase in spectral efficiency, we can get even up to 20x cell capacity. The challenge is how we can build radio units that have the same size, cost, and weight and power consumption as the radio units in the 3.5 gigahertz, while still achieving these higher capacities and using larger arrays. In 5G, we are starting to see the use of machine learning at the physical layer to replace individual functional blocks such as channel estimation, demodulation, as shown here. And in 6G, we can expect new designs for the transmit side also using machine learning. And eventually, we will have simplification or combining of these multiple functional blocks into single jointly optimized functions, both on the transmitter and the receiver, to create truly learned end-to-end learned air interfaces. There are many use cases that we can consider, such as new modulation constellations that are pilot-free, waveform learning that allows signaling with nonlinear power amplifier operation for better energy efficiency, combined channel estimation and detection, compression of the channel feedback and MAC protocol emergence and things like that. So there is quite a bit of opportunity for exploring the role of the use of the new tool such as AI in physical and MAC layer. I would like to conclude by saying that there's a lot of opportunity for us to create a 6G that's as powerful and as transformational as all the previous generations. Thank you.
Okay, Dr. Viswanathan, it was really amazing and a really interesting presentation in the technical, the point of 6G, yes. And I was really interesting to see how 5G enabling technologies, the key technologies, should evolve to 6G to create new use cases and expand the human possibilities. And also, it was really interesting to watch wedding cake for 6G spectrum and implementing massive MIMO, which you said it'll be a very challenging. Thank you so much.